Today we're going to talk about solar energy. Solar energy can be divided into two groups. You can produce electricity from solar energy, and in that case you talk about photovoltaics. And another group is solar thermal. The energy from the sun is converted into heat. There's two ways to do that. There's the active way, in which case you have a solar collector and you use it for making, for instance, hot water. Then there's the passive way, in which the building itself is designed in such a way that it harvests the electricity, the energy. And today we're going to talk about electricity. Solar cells are based on semiconductors which have a suitable band gap for visible light. And band gap is the gap between valence and conduction band. And based on the largeness on the band gap, materials are divided into three groups. Firstly, there are metals, in which case the valence band and the conduction band are overlapping. Then there are semiconductors, which have a mediocre band gap, and then there are insulators, which have a huge band gap. In these cases, with insulators, it's very difficult to get an electron excited from the valence band to the conduction band. But in case of semiconductors, we can use a photon to excite an electron to the conduction band. And in case of solar cells, the photon needs to have high enough energy to go over the band gap. So all the photons which have less energy than what is defined by the band gap cannot be used. But if we have a photon which has higher energy, for instance this high, we can still only use the energy defined by the band gap, because the energy soon comes down to this level. This actually causes the largest losses in the photovoltaics. So if we now look on what is the solar spectrum outside the atmosphere, so you can see that in the orange color. Then when the light passes through the atmosphere, some wavelengths are cut out from that, and the solar spectrum that we get to the Earth at sea level is depicted with the blue color. And then if you look at what portion of that energy a solar cell can harvest, you can see that at a certain point we cannot anymore harvest the energy. So in these cases, in these wavelengths, the energy of the photon is so small that we cannot anymore go over the band gap. And in these cases, the energy is high enough to go over the band gap, but we can only harvest the amount of energy defined by the band gap. So in these high energy photons, we cannot harvest it all. So the final amount of energy that we can harvest is here defined in the green color. And in the conventional silicon solar cells, the theoretical maximum is about 31%. Now if we look at how different photovoltaic technologies have developed. So the first solar cells were prepared in Bell Labs in 1954. Since then we have seen crystalline silicon solar cells, and you can actually see the crystal structure in these cells. So you can see these blue small crystals. The problem with these solar cells was namely the cost. And to decrease the cost, we looked at making it with a smaller amount of materials, because the materials were making the most in the cost. So that's why thin film solar cells were prepared, and in them you need only about 10% of the semiconductor in the solar cells. And the next generation solar cells are looking for a mass production. So the conventional solar cells are produced in batch, one by one. But these new generation solar cells could perhaps be prepared with mass production methods, roll to roll. You can see that the example here is rollable. And we're also looking at other materials to make them even more cheap. So next we can look at how different photovoltaic technologies have developed over the years. We have the conventional technologies in the blue color, and you can see that the maximums are actually very close to 30%, which is the theoretical maximum. And in case of such technologies, there isn't any more much room to develop them further. Then you have the thin film solar cells depicted in green color, and they have taken a lot of increase over the years in their efficiency, and they are now also reaching the theoretical maximums. In the latest years, you can also see that the emerging photovoltaic technologies, such as disolar cells and perovskite cells, have increased their efficiency significantly and are bordering the 20% efficiencies. You can also see one type of solar cells called multi-junction solar cells, or also otherwise known as tandem solar cells, reaching efficiencies higher than 30%. That is because they're based on more than one semiconductor material. So for different wavelengths, we have different material, and that basically means that you have multiple solar cells on top of each other. And that, of course, increases the cost, but in some cases the cost is not a big deal, for instance in space applications, but the total amount of cells, or the total weight of the cells. And why I'm interested in photovoltaics is that it has a huge potential. So you can see that the world's energy use is about 15 terawatts, and solar cells can produce about 1,000 times more energy than the world needs. And the potential of solar energy is much higher compared to the other renewable technologies. And also if you compare to the overall potential of fossil fuels, the solar energy has much more potential. And we discussed earlier about building a big plant of solar power. So in the map we can see how much area would we actually need to power the entire world. And that is depicted in the yellow color. And you can see that actually you don't need very much area in the world to fuel, so to speak, the entire world with solar power. And you can also see that we could utilize areas which are not suitable for any kind of habitation, or for instance, production of food or biomass. Another important thing is that if we look on where the sun irradiates more, so where the sun shines the most, it shines in the areas where there's the most population, and also where the population is growing the fastest, and where there yet isn't access to electricity. So for instance, in Africa, there is a lot of areas where people are still lacking electricity, and also in India, the population is growing really fast, and you have also very good production capability of photovoltaics. Now if we look on how the photovoltaic energy has developed over the years. So you can see that the price has decreased very significantly in the previous years. So it was very expensive, for instance, in the 70s or 80s, but now it's becoming relatively low, and it's still going further down. And and you can see also the annual production of solar power compared to years. So initially it was only used in space applications because of solar energy was so expensive. Next it was used in off-grid application in terrestrial places, so in Earth. But now already it has gotten to on-grid applications, and also it's put to rooftops and already reaching the power plant level. And you can see also the exponential growth of annual production. And here you can see image where the energy is as cheap already in the compared to electricity from the grid. So you can see that, for instance, in Italy, as I mentioned, the electricity produced with solar power is actually cheaper than the average energy price. But in the coming years, it is to be expected that many more countries will actually reach the so-called grid parity, so solar power being as cheap as the electricity from the grid. And this depends on, of course, how much annual solar energy can be produced, so the yield, how sunny it is, but also from the fact like what is the average energy price for households in different countries. And that varies quite a lot, and that has also a significant effect on where we will see energy production in the future years.